Okay, good morning, everyone, and welcome to our snacks talk for this week. I'm very pleased to welcome Dr. Alice Schwarze from Dartmouth College, where she's a postdoctoral research affiliate, I should say. Alice received a PhD in maths from the University of Oxford, and she's worked previous to that as a doctoral researcher also at UCLA. I think, was that a co-appointment or that was a visit?
It was a 2-year visit.
That's quite a long visit.
That is, if your PhD advisor moves during your PhD, that's what comes out of that.
Right, that explains a lot. And then after, she's been a postdoc at the University of Washington as well before Dartmouth. Her research interests focus on dynamical systems on networks, which we're going to see a lot of today, which is great, smack in the middle of our interest in snacks, as well as applications in biology and the social sciences. Alice is also I'm not sure the exact position, chair, director of the Women in Network Science Society. What's the exact position, Alice?
President.
President. Okay, that's even better. That's even better. I'm sorry I missed that. A great initiative as well. So, Alice, it's over to you to tell us about motifs and network inferences in linear stochastic processes. And thanks again for talking today.
Thank you for the invitation, Bill, and thank you for the kind introduction. And hello, everyone. Good morning. I always wanted to give a talk in the future, and here I am doing that. It's Friday for you. It's Thursday evening for me still. So to start your day, I wanted to introduce you to a topic that has been with me for a few years, and that's at the intersection of motifs in linear stochastic processes and their application in network inference. And so the two questions that I'm mainly interested in and talking about today is, first of all, how does network structure influence the dynamics that we see happening on networks? And secondly, can we learn the network structure from observing the dynamics that happen on it? And so there's going to be two parts of the talk that roughly focus on these two things. The first one is going to be about something that I'm calling process motifs, and that has been largely been a part of my PhD work together with Mason Porter at UCLA. And the second part is about network inference from lag correlation observed in linear stochastic dynamical systems. And that has been largely work that I've done in collaboration with Bing Brunton and Sarah Naga, who's now a PhD student at the University of Washington. And let's get started. So first of all, I want to talk about motifs and networks. And we've probably all come across the notion of a motif in a network as a small subgraph, but I want to kind of zoom out and think very big picture about what is a motif in general and how should we define it. And first of all, motifs, they don't just exist in network science or in network neuroscience or even in math or physics or something. You can zoom all the way out of the sciences. You can look at things like music, and people talk about motifs in these fields too. So for example, your system in that case would be a piece of music, and if you have a short melody in it, that is something that people who study musical pieces might call a motif. So in fact, the little piece that we see right here is actually taken out of Beethoven's Fifth Symphony, which is kind of reappearing throughout the piece over and over again, and is somehow characteristic about that musical piece. It helps us understand something about it. It helps us recognize it, and it helps us compare it to other pieces of music. We have motifs in the sciences. For example, in engineering, you could think of studying systems that are large electrical circuits, and within those you might have embedded smaller electrical circuits that fulfill certain functions. You have it in biology. If you think, for example, about the genome, which is really just a bunch of a huge system of DNA, but we know that within that there are certain reoccurring patterns that we can interpret as some sort of as the genes that are the meaningful units that help us understand what the genome is coding for. And going back to math and network science, in terms of math words, a network is usually called a graph. And if we talk about motifs, the thing that we're mostly talking about are going to be subgraphs of that graph. And maybe that comes with an asterisk, so maybe we're talking about subgraphs that appear more frequently than we would expect, given some random graph null model. Maybe we talk about subgraphs that we know to be important for a certain function of the system. But so the base kind of part of the definition is going to be a motif is a subgraph. Now I want to look at a slightly different system. I want to look at a dynamical system that lives on a network. So in other words, it's really just a coupled dynamical system. But if we talk about network dynamics, what we usually mean is that we're interested in how the coupling structure of that network affects the dynamics. And so in that kind of system, this is something that is qualitatively different from just looking at a graph. A graph is a static object. And if we look at smaller parts of a static object, those are also going to be static objects. It makes sense. But now that we're looking at a dynamical system on a graph, that is a dynamic object that has temporal properties. And so perhaps the smaller units of it that we're going to use as motifs that help us understand the system might not actually be subgraphs, but might be something else. And so throughout the talk, I might call these smaller units process motifs. I might call them microprocesses, which especially for people who don't like talking about motifs might be the more intuitive way to talk about them, but I mean the same thing if I say it. And so the first half of the talk is really just about how we define it and why I think the way that we're defining it here is a sensible way to do it. So let's get started with that. So I'm going to first start by explaining what a process motif is, by explaining what a process motif is not. And that is in comparison to structure motifs. So structure motif is what we had on the slide before as a motif in a static graph, where the thing that we care about is the structure of the graph. So we're going to care about small pieces of that structure. And to do that, we're going to define a structure motif as a small graph and an occurrence of a structure motif on a certain given larger graph as a subgraph of that larger graph that is isomorphic to our structure motif. Now that's like a bunch of words, and I think I have an example here. So say we have a digraph that has 6 nodes, and I think 1, 2, 3, 4, 5, 6, 7 edges. And let's say we want to look for smaller graphs in that larger graph that might help us understand something about it. So say the smaller graph that we're interested in is just this directed 2 path over here. So now we can go into this larger graph and look for occurrences of this motif. So here's our motif. And in the colors, with the different colors, I've indicated where we can find an occurrence of that motif. Occurrence meaning a subgraph of that graph that matches the 2 paths that we have over here. And so, for example, one of them is this blue one over here. So these 2 blue edges together form a 2 path. So we would call them an occurrence of this motif in this network. Now, moving forward to process motifs. In my PhD work, Mason and I defined a process motif as a connected, directed, and weighted multigraph in which each edge represents a walk and each edge weight represents the length of a walk. And an occurrence of a process motif on a larger graph is a labeling of the nodes and edges in the process motifs, so that it matches the nodes in the larger graph. And so again, we have some examples for that. So for example, I'm looking at a very small graph now. So we're going to start with this graph over here. And basically the question that we're asking is, on this small graph, what kind of processes can happen on it? And so here are a few examples of what might be feasible to do on this structure. So one thing that you can do in the structure is walk one step from one node to another. So that would be a motif, a process motif that can happen on this graph over here. And an example of an occurrence of such a motif is a labeling where we label this node as I and this node as J. And so we see that this is possible, right? I can start at I can go one step and I arrive at J. Now we can look at more complicated processes. So for example, we could have a circular walk of length 2. For kind of bookkeeping purposes, there's actually having another walk where these two nodes may or may not be the same node is a different category of motif. We can have motifs where we start at some node and maybe at some different node or the same node, and there's two walks that take us to another node. And so an example of that would be we have two walkers, both start at node J, and they go to node I in one step. So that is definitely possible to do over here. And there's a bunch more that we could think about. What I want to point out at this stage, and we're going to come back to that later when we're doing network inference, is that this all seems very complicated, but it's in part complicated because we're looking at a recurrent network. So we have cycles in the network, and that means we can basically keep walking on it forever. So there's an infinite number of possible microprocesses that could happen on here. But as soon as I cut the cycles, and so we're left in this case with just a graph that has two nodes and one edge, it's a directed acyclic graph, the only process motifs that are left, so the only process motif that is left is actually this one over here, and it has a single occurrence on this network. So there's really just one process that can happen on this small graph, and that is you go from I to J in one step, and then you're done. And so we'll come back to that in a bit. Now, in the meantime, I want to talk about why we would want to define motifs and dynamics on networks at all, and in the way that I've just introduced. And so one thing is that when we study dynamics on networks, a lot of the models that we use end up being linear differential equation models. And for these models, we can actually think of the emergence of, certain properties of these systems as being emerging through microprocesses that all happen at the same time. So for example, if we look at something like a chemical reaction network, and we're looking at how concentrations of certain chemicals increase or decrease in that network, we can really think about it either like on the macroscopic sense of kind of measuring concentrations in one petri dish or another. But what happens at the base level is that there's molecules bumping into each other and undergoing chemical reactions are not unlimited. So in that sense, you have microprocesses in that chemical reaction network from which the global dynamics emerge. And you can think of other examples too. So for example, if you're looking at things like traffic networks, if you're interested in the level of congestion at certain street crossings or something, then these are of course macroscopic properties that you're looking at, but there's underlying microprocesses that are just cars running along your network and stopping at intersections or something like that. And so these, through some of the movements of the cars, you get those macroscopic properties like waiting times and congestion and whatnot that you're interested in. So in all of these cases, what I'm thinking about is modeling it by dynamical systems, specifically ordinary differential equations that might look something like this. So we have a state vector X that represents the things that go on at each node, and we have some dynamical system that depends on the coupling structure and the current state of the system. I've talked a lot about dynamics without having actually introduced any dynamical system to you at all. So I'm going to make up for that now. Here we have the Ornstein-Uhlenbeck process, which is a linear stochastic continuous time system. One version to write it down is this one over here. So we have that at every that the state vector changes incrementally based on the coupling structure with some coupling parameter over here, and some noise that is regulated by some noise parameter over here that I call sigma. And we have a time scale parameter in here that I call tau. So if tau is really large, then the system takes a long time to decay back to its its statistics steady state. If tau is really small, then it usually decays down, it decays back to its steady state really fast. So this is a continuous time model, and I've put something on the slide here that I call memory built in. This is going to be relevant when we're going to compare it to discrete time models in a bit, but just keep that in the back of your head for now. What I want to talk about right now is that this stochastic differential equation is really, really nice. First of all, it's because it's been really well studied and it's got a lot of applications and stuff, but also because there's a ton of stuff that you can do with it analytically. So for example, you can get its steady state covariance matrix analytically. So it has a statistic steady state at 0, meaning we have a steady state distribution that is a multivariate Gaussian centered at 0. And for that, we can get the covariance matrix analytically by doing some calculations over here. And there's somewhere in the appendix of my paper, there's somewhere in possibly the appendices of a dozen of Joe's papers. So like, if you have questions about that, just bug Joe about it at some point over coffee with real snacks. But what I want to do here is look at this equation. So what we have here is we have the adjacency matrix and its transpose go into computing the covariance matrix. And we have some scalar factors over here that depend on the parameters of the system and the powers that go into this matrix power over here. Now, we can interpret this matrix power as a count of a set of walks in the system. And I'm running out of battery, which isn't great. Just a sec.
You're right. Take your time. I'll just pause the recording while you do that.
Okay. So I wanted to look at this term that's the powers of adjacency matrices. So we know that if we take something like the Lth power of an adjacency matrix, the elements of that matrix, of the resulting power matrices, are going to tell us in how many ways you can walk from one node, from node I in the network to node J. So that's what the ijth element of that matrix power is going to tell us. Now, if we have a combined term like this one over here, where we combine the power of the adjacency matrix and the transpose of the adjacency matrix, what that corresponds to is something like this, where you start at an unnamed source node, and you go in some number of steps that is, in this case, lowercase l to node I, and in some other number of steps that is, in this case, uppercase L minus lowercase l to node J. And the reason that I chose this very wordy notation is that the uppercase L is going to tell us how many steps those walks in the microprocess sum up to in total. And the lowercase l is going to tell us how long one of the two walks that we have in this microprocess is, what the length of that walk is. And so we can interpret this equation over here as saying that there are a bunch of microprocesses that happen in the Ornstein-Uhlenbeck process, and each of those has some contribution to the covariance matrix. And how large that contribution is depends on the shape of this microprocess as given by uppercase and lowercase l, and the parameters of our dynamical system. Now, there's a bunch of really intuitive stuff that comes out of this. Now, first of all, if we just look at the shape of that, there's already something intuitive in saying that what things cause covariance or correlation in the system. And you've probably all heard the sentence, oh, causation isn't correlation, or something like that. And so you see that illustrated here as in sort of a graphical motif language, where you could set lowercase l to be 0 or to be equal to uppercase L, in which case this motif is just going to simplify to being a walk from I to J or from J to I. So what that means is that there's a bunch of processes that contribute to covariance in a system. And these include direct causal chains going from I to J or from J to I. But there's also a bunch of other processes that involve some sort of confounding factor that influences both I and J at the same time. And if we plot out the contribution of each of these motifs, we again see something quite intuitive in that process motifs that have overall a small number of steps, so small L, which would be this region over here, tend to contribute more than process motifs that are very long. So we have many steps to take to realize that process. And this is simply because the way that the Ornstein-Uhlenbeck process is built, we have a signal to noise ratio that decreases with every with the propagation of signals along edges. So if your signal has to travel a very long time to get to where you want it to go, then you're going to lose some of that signal to noise ratio. And so you're going to end up having a small contribution to covariance over here. The other thing is that in this corridor over here, the yellow one, these are the process motifs where you take roughly the same amount of steps to the left and to the right. So this walk and this walk have roughly the same length. And for a given number of total steps, those are the processes that contribute the most to covariance, simply because to have a strong contribution to covariance in a system that is returning to its steady state over time, so a mean reverting process, you want those signals to arrive at the two nodes at roughly the same time. And so you can do the same thing, not just for covariance, you can do that for variance by basically just looking at the diagonal elements of the covariance matrix. You can also do that for correlation, which is covariance divided by the variance at the two nodes. And so this looks perhaps a bit convoluted, but what it really is that we have a process motif for covariance in the middle, but connecting the two nodes I and J, and then we have a bunch of process motif for variance at both the node I and the node J. It's hard to keep track of all that, but you see some sort of intuition evolving from this, in that we can see how correlation is related to covariance and variance in the system. I'm going to skip this for now so we can talk about the contributions to correlation as well, and some of them end up actually being negative. You can also map those process motifs back onto structure. So by basically saying, okay, let's take a small graph, and as we did in the beginning, enumerate all of the microprocesses that can happen on this graph. And sum up the contributions of all of these microprocesses and use them to define contributions of a structure motif to a certain, to covariance in the system. So we can do that for covariance and correlation. And we find, again, a mix, in this case, a mix of intuitive and perhaps not so intuitive results, where we have a bunch of motifs that end up having a positive contribution to covariance, and all of them involve that there's something like a path from node I to node J. In some cases, you might have a third node that sends a signal to both I and J, and that has a positive contribution to correlation and covariance. Interestingly, there are some motifs that have a net negative contribution to correlation, and that just comes about from having, for example, other nodes pollute the system and thereby decrease the signal to noise ratio, as you have in this case over here. So if you're interested in increasing the correlation between a node J and I, then on one hand, J having to send a signal to I, that is great to help with correlation, but then having another node sending an independent signal to I is just going to lead to a lot of noise at node I that is not going to help increase the correlation between nodes J and I in this case. So to conclude that first part of this talk, we talked about defining process motifs or microprocesses that help us understand how dynamics on networks are related to a network structure. For these process motifs, we can derive their shape, and we can derive their contributions to covariance and correlation, and to several properties that are functions of covariance or correlation. And we can use that in turn to go back to smaller subgraphs and say, how do these subgraphs, do we expect them to have a positive or net negative contribution to the covariance or synchrony or something in a system? And we find that some of them do actually have a negative contribution. So increasing the connectivity in your graph is not necessarily going to always increase the coherence in your system. That is something that people have already known, but this angle via the motifs gives you kind of a bottom-up way to look at this problem and to make it make sense. Now, I was pretty proud of that part of my PhD work. Maybe you can tell by the way that I get excited talking about it. When we sent it in the first time to a journal, it came back pretty quickly with the comment for, well, that's nice, but it hasn't got any like foreseeable application, so it's probably not going to make a difference and we're not going to accept it. I was a fierce PhD student and very upset, and so as a gotcha, I did a postdoc in data science and wanted to find an application for what I did during my PhD, and I found it in network inference. So first of all, the setting that we're considering here is that we start with an unknown network. There's some nice, easy dynamics running on this system, and we can observe all of the nodes in the system. So we know all of the nodes, we just don't know how they're connected. And by observing the nodes, we get something that I'm calling a time series data set. It's a rectangular array of data. And then we want to do some data science magic to that data to end up at something that is, if not exactly this network structure, pretty close to it. So this is what we want to do. And that data science magic throughout this talk is going to involve something that I'm calling a score matrix. So basically, we're going to compute some number for every pair of nodes that is going to tell us something about how likely it is that there's an edge between those two. There's an obvious caveat to that it assumes that we can do these pairwise comparisons independently of each other, which is not necessarily true for network dynamics. But in terms of things that could reasonably scale to large networks, it is probably one of the few things that can actually work. And it is one of the approaches that, or it is probably the approach that gets used most in network inference, because there's a bunch of things that you probably already know, like using Granger causality, for example, to infer networks. And so all of these fit into this category of there's a score for node pairs that you compute, and you're going to use that score to decide where to place an edge or not in your network inference step. So what I'm going to do now is I'm going to compare two different dynamical systems. So we had the Ornstein-Uhlenbeck process from before, but especially in constructing networks from multivariate time series data, another process is very frequently used, which is the vector-autoregressive model. This is also a linear stochastic process. It is different in the sense that this is a discrete time model, this is a continuous time model. Here the E is conventionally, like, it's called error because you usually try to use this model to fit it to data, but you can think of it as equivalent to the noise term that you have over in the Ornstein-Uhlenbeck process. You have at least one adjacency matrix. Because it's a discrete time process, it might make sense to think of edges that take a longer time to traverse. So you could have, say, A with the superscript 1, those are all the edges that you can traverse in one time step. You could have a second adjacency matrix that collects all of the edges that you can traverse in 2 time steps. And so you can go all the way up to some order P, which is going to be the maximum edge transmission length, the time length that you're going to consider. So this is a discrete time model. And in contrast to the Ornstein-Uhlenbeck process, this has no memory built in. So what I mean by that is that if we say we run the system with an empty graph, so the adjacency matrix is just going to have zeros everywhere, then in the case of the vector-autoregressive model, what we get is zero autocorrelation except for, well, the signal with itself at time 0. Whereas in the Ornstein-Uhlenbeck process, we get an exponentially decaying autocorrelation function. So that means that even on an empty graph, the signal is correlated with itself from the past positively. Whereas in the vector-autoregressive model, on an empty graph, that's just not true. And so that can lead to interesting effects where this one kind of nicely converges down to the zero line. And here you can create some nice little examples where you get these jumpy timelines where signals kind of nodes basically turn on and off like in a Boolean kind of network sense. So we wanted to study both models and to some extent see what difference do they make when I use one or the other in the way that I generate data for the network inference problem, and what happens if I mismatch, and then you assume the other model for when I try to actually do the inference from the simulated data. So to bring all of this together under the hood, we came up with a stochastic delay difference equation, which nicely interpolates between the Ornstein-Uhlenbeck process and the vector-autoregression. So this is this equation over here, which looks quite similar to the other two that we had before. In this equation, we have the time step, delta t subscript tau, which measures basically is a measure of how autocorrelated the signals are in my system. And if that parameter goes to 1, we exactly retrieve the vector-autoregressive model, whereas if that parameter goes to 0, we retrieve the Ornstein-Uhlenbeck process. So I just said it's a measure of how autocorrelated the signals are. I think like the inverse of it is actually the measure of how autocorrelated the signals are. That makes more sense. So, and for this process, as well as for the vector-autoregressive model and the Ornstein-Uhlenbeck process, we can again look at correlation, covariance, lag correlation. We can do lag correlation now because it's a discrete time system. And we can ask, how do certain processes, microprocesses, contribute to lag covariance in the system? So here we have a few examples of some process motifs and their contributions to covariance, lag covariance with a lag of 1, lag covariance with a lag of 2, and with a lag of 3, and so on. And you see that all of these motifs end up having slightly different contributions to each of those, and all of these covariance matrices, you can think of them as being represented by some linear combination of the counts of these motifs. And for example, for covariance, a strong contributor to that linear combination is this microprocess over here, and these two as well, and this one not so much. Whereas if we're looking at something where we have a lag covariance with a lag of 3 steps, that changes a lot, and so we have still a strong contribution of this process motif that is just a walk from node j to I, but we have much smaller contributions from, for example, this confounding factor motif, where we have some other node from where we take 1 step to node j and 1 step to node I. And these also depend on how we choose the parameters of the system. So these contributions can vary. Now, I'm going to try to explain how this relates to network inference. And so what we want to do is we want to compute something from the covariance or correlation matrices that is going to tell us whether there's an edge between a pair of nodes. And in an ideal case, what that would look like in those diagrams that I just showed you is it's going to look like this. So this would be our ideal score to use to infer networks. And that is because whenever this score would be positive, we would know that there's a microprocess where there was some signal taking just 1 step in the network to get from node J to node I. So if that happens, if we can say with certainty, okay, this quantity f is non-zero, therefore there must be a walk of length 1 going from j to I, that means that there also must be an edge going from j to I. So if we had a measure like that, we could perfectly infer the network from it. Now, we don't, and I think I wouldn't believe myself if I claimed I did, but we can see how covariance or even lag covariance is a very imperfect measure of the likelihood of there being an edge, because there's so many other processes that contribute to lag covariance. So if I compute the lag covariance matrix for my multivariate time series, then if I get large values in there, it could be because we have a motif like this and ergo an edge, or it could be that we have a bunch of other microprocesses happening that maybe look like this, and they also give us a strong lag correlation between a pair of nodes. But something that we can do is we can say, well, we have the covariance matrix, we have the lag one covariance matrix, we in principle also have other lag covariance matrices. So why not combine them in a way that brings us closer to this ideal case over here? And so this is basically all that we did. Now, it turned out that for numerical reasons, it made sense to use the correlation matrices rather than the covariance matrices, and to focus on the lag 0 and the lag 1 covariance matrix, because they are most stable even for short time multivariate time series. And what we do with them is we either combine them in a way that we have a 0 contribution from this motif over here that we associate with reverse causation. So this is relevant if you have a network where you expect a lot of non-reciprocal connections, where you want to make sure that just because I is talking to J, you don't falsely infer that there's also a connection from J to I. So this is going to be very unlikely if you use this linear combination of lag 1 covariance and the covariance matrix as your score for inferring networks. The other thing that we tried was to say, okay, we want to get rid of these confounding factor motifs where we have a different node that talks to both I and J, and we don't want to falsely infer edges just because of that. So that would be more relevant if you have, for example, a highly clustered network. And here we have combined, we've chosen the value of alpha such that the contribution of this microprocess goes down to 0. So we put it to the test. We generated a bunch of really random graphs. We simulated the dynamics on it using the stochastic difference delay model. And then we tried to infer networks from it by using one of the linear combinations that we proposed, by using vanilla lag correlation without any correction to it, by using convergent crossmapping, a very simple transfer entropy estimator that was implemented in the netrd Python library, linear Granger causality, and something that in the library they call inference, which is just computing the inverse of the covariance matrix. And so in these plots, whenever you see something blue, it means that just by doing the simple correction to lag correlation, we were actually able to infer the networks with higher accuracy than the method that we compared to. If you go into the red regime, that's where the method that we compared to was able to infer networks with higher accuracy than we were. Now these plots show a lot of blue. I'm going to just add the disclaimer that how much blue and red you get absolutely depends on how you choose the parameter space that you're testing out. So for example, if you would have said we only look at systems that have a really high coupling strength, and we're not interested in systems where we have different delays on the edges, we only care about the case that all edges have a transmission duration of 1 time step, then we could have really focused in on this regime over here where linear Granger causality cannot compete the method that we proposed. But I think it's what this is supposed to show that is that there are a lot of use cases for the simple correction that we proposed here in comparison to a bunch of other things that you can do. Well, I'm also going to point out that what we did was we literally just subtracted 2 covariance or correlation matrices from each other. This is incredibly fast to do. all of these methods over here take a lot longer to run than what we did. Another thing that we saw when we were kind of going through several axes of this large parameter space that you can look at, and it's really large because there's things that you can change about the dynamics that you run on the system, such as the characteristic time of your dynamics or the coupling strength. You can change things about the network structure that you're trying to infer. So maybe you know something about the density of edges in your network, but you know how large your network is, or you know the reciprocity of edges, and so on and so forth. So we tested a bunch of these things. What we see is that a lot of these methods that we tried out, they behave very similarly on a qualitative level. So really, there's always a slice of that parameter space that you can find where your method of choice is going to outcompete the others. But there's some general statements that we can make in the sense that signals with a very high characteristic time, so a lot of autocorrelation, positive autocorrelation in the system, those tend to be harder to infer than systems that don't have that. Systems with high coupling strength are easier to infer than systems with a low coupling strength. Large networks are more difficult to infer than small networks. And in terms of edge density, if you're somewhere in the middle between 0 and 1, those are the interesting networks to infer, but also the hardest. If you know your edge density and you just threshold right in a very sparse or very dense network, you get a lot of accuracy for free, and this is what this parabola shape of the baseline accuracy tells us. One advantage of having a method that can infer networks with a decent accuracy really, really fast is that we can run a bunch of test cases, and understanding that there's certain things about the local network structure that can make or break the network inference is also helpful in understanding which network structures end up being very easy to infer and which network structures are much harder to infer. So here we have just a small example of what we call shooting star networks. So all of these are networks that consist of like one long path. That's the tail of the shooting star. And then we have a star-shaped network that's at one end of that path. And so we built a bunch of these where we've had some fraction of the nodes in the head of the shooting star and some fraction of the nodes in the tail. And it turns out that if there's roughly the same number of nodes in both the head and the tail, those end up being the networks that are the most difficult to infer. That's got something to do with essentially as you threshold your score values, whether it's Granger causality, transfer or lag correlation, your edges are kind of in competition with one another, your potential placements for edges. And it turns out that especially if you have large heads of the shooting star, that these nodes that are part of the head tend to have signals that are highly correlated, even when they're not connected. And so what you typically see as you infer networks is that some of the edges in the tail of the shooting star end up missing, but you instead get more edges that shouldn't be in the head of the shooting star appear in your inference. So there's probably more to explore here, and we're just kind of really happy at this point that we can do that all with basically on the laptop that I'm talking to you right now with almost no computational power at all. We can run a bunch of these simulations and hopefully learn about which parts in the network structure are the ones that give us a hard time when we infer networks, and hopefully guide the way in terms of finding out what we can do in the future to do better about inferring networks from time series data. And so to conclude the second part of my talk, I've introduced the stochastic delay difference model that interpolates between the Ornstein-Uhlenbeck process and the vector-autoregressive model. And we use the process motif contributions for the stochastic delay difference model to make some corrections to lag correlation. And these corrections to lag correlation can help us correct for reverse causation or confounding factors and give us good results for network inference across a very wide space of the parameters that we can consider here. And having this inference method that is directly related to motifs and networks can help us pave the way to having some graphical explanations for what are the limitations, or what are the strengths and weaknesses of current network inference models, and how can we address them in the future. And so with that, I would like to end, and I'm happy to take any questions.
Thanks very much, Alice. Now, one thing I should ask you before we start the questions: do you want us to stop the recording before questions, or keep that free?
Oh, we can keep it going. That's fine with me.
Okay, cool. So, if you've got a question, please either put a hand up or throw something in the chat. And I can ask it for you if you put it in the chat.
I have one.
Go for it.
Yeah.
The SDD seems very general and very useful. And it's kind of shocking to me that no one's ever written that thing down. Is it true? Is this a new, no one's ever thought, oh, we need autocorrelate, autocovariance and covariance, Einstein-Ullbeck does the covariance, VAR does the covariance without the auto, let's add in a bit of auto. Like if this is the first time that's been done, because I've thought about that before and I've never found a way to do both, and here it is. Am I missing something, or is this big?
Well, I hope it's big, and I hope it's good. Obviously, like, I could be wrong about that. We wrote it down, and like when we did it, it kind of, like, at first sight felt like an embarrassing crux to me to do it. I've given a similar version of this talk in other settings, at math conferences, where the feedback that I got was, oh, you're trying to interpolate between discrete time and continuous time systems. That's provocative. Which, said by a British person, is not a nice thing to hear. So maybe it's the provocativeness that has kept some people from doing it, because I think like from a math dynamical systems perspective, it's a bit dirty to try to interpolate between discrete time and continuous time systems. Like, those are supposed to live in separate cages. But I could be wrong. Maybe like, especially with this audience, with people with different backgrounds, maybe somebody goes like, I've seen this before. It's been here since the 1980s or something. And like, if that's the case, please tell me now, because like the final version isn't out yet, so we can still add citations.
But would a VAR process just with coefficients along the diagonal, wouldn't that give you some level of autoregression, autocovariance? If
you have values along the diagonal, yes. I think the difference is for network inference that suddenly those start counting as edges. So they're suddenly in competition with the rest of the system as potential places to place edges. If you know that your system is already autocorrelated, you want that information baked into your model before you do the inference, because it's otherwise just another potential source of error.
I see.
But it's not just about adding edges to the self edges. If you go back to the first motifs that Alice was showing, where you've got say for the covariance, you've got those two different path lengths that I think there was capital L and capital L minus little l. Having those two different lengths contribute, that's a signature that you get that in continuous time because of the autocorrelation that's there. In discrete time, you get different ones showing up. And even if you stack a lot of self edges in, you just don't see the same ones recur. So it's fundamentally about those autocorrelations that are baked into the equations that make that come through. You can start to put in things like self edges, but it's still not the same. yeah, I really like this idea of having something that interpolates between them. When you first started presenting that equation, I thought you were just presenting a discrete time approximation to the continuous time, which is a known thing to do with that square root of the noise term and so on. And then suddenly it was apparent that you were looking at a more generic model that interpolated between the two, and I think that's really nice. It's as you guys said, they are fundamentally different at the extremes, but why shouldn't we explore? Why shouldn't we explore the dynamics of what happens in between them? That seems like a really nice question.
Some people like being provoked.
I'm glad that this crowd likes to be provoked.
We like being provoked, yeah.
We have a question from Leo. Take the floor.
Great talk, Alice. Enjoyed it. I haven't had a chance to read the latest paper, the preprint, but that's a really nice introduction for sure.
Well, now you don't have to read it anymore. That's everything in there.
I was wondering, how do you approach the thresholding part? Because that's always one of the tricky things we have to deal with when you compare. Also, how do you compare different methods? Like, do you use the same threshold for all when you did your comparison? Just can you expand on the thresholding part?
Yeah, we cheated our way out of that. We said that there's an oracle telling us how many edges there are supposed to be. So we already know the number of edges. We just need to find where to put them. And one of the reasons that we did that, so there's two reasons. One is that I don't like developing statistical tests, but the main reason being what you said, that different statistical tests would be appropriate for different ones of the methods that we tested, and then the whole comparability kind of becomes very unclear whether you can still do that or not. So in this case, we assume that there's an oracle who has told us already this network has 50 edges, go find them.
Right. Yeah, as you say, it's not fun to develop statistical tests. I can relate. We did a few.
But you've done that in the past, right? I think there was a paper where you did something like that for transfer.
Yeah, there's a whole paper about that. Yeah. It's good in the end when it starts working, but yeah, developing it, it's tricky. You need to do a lot of testing, and we ended up using a greedy thing where you start including some I don't know, I don't know if there's a straightforward way to just apply that. I was also curious if this approach could be used with motifs that we derived with Joe for transfer entropy. In principle, it should be the same core idea. It doesn't necessarily matter if it's correlation or covariance, but maybe Joe has more well-defined questions around that part.
Yeah, probably even less well-defined. I mean, if you want to address anything Leo said first, then I can chime in afterwards.
So I think this is all great feedback. And like Leo, if you ever feel like developing another statistical test, we can look into whether we can make a sensible one for corrected lag correlation, because I have no idea like how to start doing that. So as you pointed out, one thing that I like about it is that, first of all, you can correct for any motif that you want. So I hinted at, we've corrected for reverse causation in one case, we've corrected for direct confounding factors in the other case. You could decide that depending on which motifs you expect to find in the network the most, that you make dependent on that what motif you want to correct for. So for example, if you know that your network has a bipartite structure or something like that, there might be different motifs that you wanted to correct for. And so that's something that I really like from building these methods up, like bottom up, and understanding what the limitations are. And I think, you should be able to do basically the same thing for transfer entropy, right? You had that transfer entropy motif paper as well. The motifs looked very similar to the covariance and correlation motifs. So perhaps you end up having maybe even the same numerical values, but some constant or something like that. But like, if you can get the motifs, you can get correction factor. You can do the same with transfer entropy, I think.
Yeah, it's interesting because transfer entropy, it's that one of them, one of the main points of why it's used in the first place is that it's directed. So maybe it already deals a bit with the, maybe you don't have necessarily to correct for the reverse direction as much. I don't know. I really don't know. It's just, I'm really just brainstorming.
One thing that maybe Joe can comment on is that, so this is all limited to linear stochastic processes. As soon as they become nonlinear, we would need to do something about essentially linearizing them again, because the whole idea of motifs adding up to something that only works in linear systems. And as far as I remember, we did have some discussion about transfer entropy in linear dynamical systems and how that kind of ends up being very similar to Granger causality in one way or another already. So I'm not sure to what extent we would expect Granger causality, transfer entropy, and lag correlation not to be very similar in linear systems anyhow.
Yeah, you're right. Our derivations were all under the assumption of linear Gaussian linear systems effectively. So it would be VAR. We did, however, you can't really do, at least we couldn't do many derivations with nonlinear, but we tested on nonlinear systems, and some features, like, for example, when you mentioned that if the target node has other incoming links, they kind of inject more noise and corrupt the measurement. That kind of phenomenon where if you have a high in degree of your target node, that makes it harder to infer. We found that even in nonlinear systems, so that we call it the in degree effect or something like that. So some of these seem to translate. I think that's the effect that translated it was most clear translation. Other didn't as neatly in nonlinear systems, but yet, as you say, it's very hard to do any derivations. Yeah, with that. But I like going back to some of the things you just mentioned. That I like how you can put in knowledge about the system, as you say, if you know that it's bipartite, or if you know that you shouldn't expect bidirectional links. I know how your method has a way of, that you can put in some of that knowledge. I think that's a nice feature. Sometimes I'm not entirely sure how to put knowledge into some of the algorithms we have. Obviously, you can start with a conditioning set that if you know it beforehand for certain nodes, so that's one way to do it. But there's different types of knowledge that it seems you can incorporate in your algorithm. So I just thought it was a nice feature.
Thank you. I'm glad that you like it.
Thanks.
Just picking up on some of what you and Leo were talking about with the Granger causality transfer entropy relationship. So in this kind of dynamics where everything's linear, transfer entropy and Granger causality should be equivalent in theory. If you've got enough samples with any transfer entropy estimator, you should get the same value as Granger causality. Obviously, you're dealing with limited samples. You're dealing with different differences in estimators. So for finite sized number of samples, the transfer entropy isn't going to do as well as Granger causality because the model isn't as good for what's going on. So Granger causality, you would expect to do much better here. That's one thing. The other thing I wanted to come back to was kind of a big picture interpretation of the comparison here of the new method to those different pairwise methods. So, kind of in building in, I'm not even sure what the right nomenclature is, but in building in those, those weights that you have, like you're kind of starting down the path of considering multivariate effects. Like it's not fully going down that path, but it's starting down that path. And that's where the real difference comes from. Like the pairwise methods can be subject to all sorts of confounds from common drivers, from pathway effects, from this and that. And that's exactly what you're targeting with bringing in these weights. So, I see that as the real big picture explanation of the differences here. What I'm super curious about, as Leo kind of hinted, is can we bring in something similar when we go fully multivariate? Can we bring in some of these sorts of things like that? And that's a very big question. That's a very
What do you mean when you say fully multivariate?
So like with this greedy algorithm that Leo and I have been working with the transfer entropy and Granger causality, which is designed specifically to remove redundancy, remove redundant connections that are similar common driver effects and so on. And it does fairly well handling those confounds. But you know, I wonder whether there are aspects we can bring in like this into that multivariate algorithm, if that makes sense. Like at the moment, you know, you're bringing in those weightings. It's kind of bringing them in, dealing with the pairwise. I wonder if there's a way to step it up, to think about, you know, at the multivariate level. Does that make sense?
It does make sense. I would hope that the answer is yes, but it's also like I have no idea.
Yeah, that's a big question.
It's always like the proof of the pudding, right? You got to try it out. See if it works. I guess you could just. I've worked enough with computer scientists now that I know that there's one solution is always to just throw it all into a big neural network and see if it improves your results or something like that.
Now I have more questions.
Hopefully there would be a more like I personally like when things are not that black box. So like I think the more elegant solution would be to think really hard about how to translate this into a multivariate setting and hopefully get something out of that. Yeah.
Now I've got more questions, but I don't want to dominate the floor. Would anyone else like to jump in?
My questions are quite naive, but I was also going to wait till the end for that reason.
Would anyone else like to ask anything, or should we let Ben ask his naive questions?
I like naive questions.
Oh, good.
Especially when they come from people more senior than me and more senior than some others in the room. It's good to know that everybody has naive questions.
A few softballs. Okay. Well, no one's got it. Maybe if you go back to the summary of part 1, that has the two that I was unsure about. Yeah, the one on the right there in the middle is the correlation one, right?
You mean this one over here?
Middle on the right, yeah. I was just, you know, my a priori would be if it's a correlation, it's going to be symmetric in I and J, but that graph is not.
It's so in the vector-autoregressive model, it would be symmetric. In the Olmsted process, it doesn't have to be because of autocorrelation. So you can have essentially signals can run through a longer process on one side than the other side, but you still have some effect that has on correlation. Your intuition is correct in the sense that the strongest contribution or the largest contribution that you're going to get are the ones where either you have, first of all, very short processes going on both sides of this this motif. So in fact, all the motifs that contribute to covariance also contribute to correlation. Those are just some where you don't have any process motifs for variance being part of that motif in the end. So you can have anything between 0 and an infinite number of rings on both the nodes I and J. And if you have no rings at all, you get the strongest contribution. If you have rings, then you get larger contributions if you have the same number or like similar size of rings at both the nodes I and J. So in that sense, your intuition is right about this. And the reason that you do get contributions from motifs like this, where you have more rings or like different sized rings at both nodes I and J, is because you have that autocorrelation in the system. So there could be a signal doing like something over here at node I, and it's been done with the whatever walk it has taken 5 time steps ago, but it still has some, because of autocorrelation, there's still some correlation between nodes I and J in that case.
Okay.
But yeah, like the diagram here is not indicating that there are supposed to be more more closed loops for node J. This is just a sample, right? Like it's not sort
This
of
is a
saying,
sample, but you can add or remove as many rings on both sides as you want. So I chose the asymmetric example to show like all of the things that are possible, but having the same number of rings on both sides is fine. Having no rings at all is also fine.
Yep.
Having rings only on one side is fine. It just varies how much contribution you get.
This is a contribution. Yeah, okay. Yeah. And in that bottom one, the J one makes some sense.
Yeah.
You'd think that even in that one, just not having anything from J to I, oh, they all have to have something between them, don't they? But then K and L make less sense that they would detract from.
Okay.
Right? Wouldn't
So
K be
there's
like
this.
the massive contribution would be K, you'd think. Huh?
There's some subtlety to how we define these contributions. So those values, the C's with the hats, those are the contribution of all microprocesses that can happen on this graph, but not on a graph that is smaller than this graph. So this is the contribution that you get from having a bidirectional node edge between nodes I and J, minus the contribution that you get from having a unidirectional edge from node I to node J, and minus the contribution that you get from having a unidirectional edge from node J to node I. That was a lot of words, but so what these pictures are trying to tell you is something about some synergy of these edges. So you know that having an edge from I to J or from J to I is going to give you a positive effect to correlation. What is the added kind of network type effect that you get from having both of them in at the same time? So what this is telling you is that you get some contribution from having an edge from I to J, some contribution from having an edge from J to I. This motif over here seems to have less than the sum of these two. So somewhere, some of that correlation went to the buckets. And this is what the negative contribution of this process motif tells you. And the reason that it happens is that by having that bidirectional edge, you have created an infinite number of cycles at every single node that increases the autocorrelation of the signal at each node.
Yeah, that's subtle, isn't it? Okay, I understand. Yep. All right, thanks.
Yeah, we had similar things when we looked at the motifs promoting transfer entropy in Leo's papers. You know, you get sort of the lower order terms that are the ones you expect, and then at higher order, suddenly you see things like this that are contributing negatively. And you know, Alice said it exactly right. Like it's kind of a correction factor that, you know, the overall lower order one is going to have the main effect, but then you've kind of got to have this correction because of, as she says, autocorrelations that are there, or what have you. Do you have any more questions, Ben? Okay, cool.
No, got it. Over to you.
All right. Alice, can you come back to the slide where you start digging into the method and you've got the, I guess it's a vector of the weightings that you apply.
So I have this one, and then I have these over here.
Yeah, perfect, perfect. So at the moment, it's just looking at, as you said, the sort of zero order covariance and the covariance lag one. So you've kind of hinted that, you know, these are some weightings that you've applied to handle specific situations that you have in mind. So I guess you were going to look for, if you're going to look for links that work on a lag of 2, say it's discrete time, we're looking for links on a lag of 2 or a lag of 3 or a lag of 4, you would redesign your weight vector here and take into account longer order correlations. Is that correct?
Yes, so I would replace the lag 1 correlation matrix by a lag K correlation matrix, and I would replace the lag 0 correlation matrix by a lag K minus 1 correlation matrix.
Yeah. Is it that simple, or would you have to include some terms at the lower correlations as well? And
I was surprised, but it's actually that simple.
oh, okay, yeah.
So that there's just a bunch of things that end up canceling out. One interesting thing that I can say about this as we're going into the weeds is that I tried having linear combinations of more than 2 lag covariance matrices, because I thought, oh, if I plug in more, then I can set more of these contributions to 0 and say something like, if I have infinite covariance matrices, then I could get perfect network inference. And maybe, like, in theory, you can do that or not. But what happens in practice, even as you try to get more than the lag 0 and the lag 1 covariance matrix, so more than 2 in your linear combination, is that if you interpret these contributions as kind of vectors when you're doing the linear combination of, it turns out that as you move to higher lag times, that these are not exactly, but very closely to being linear dependent on the ones that you already have. And so you can't get a good correction, you can't get a good improvement of adding, say, the lag 2 covariance matrix to this equation over here without having really, really large coefficients in the linear combination. And so in theory that might work, but in practice, just because these are not steady state covariance matrices, these are sample covariance matrices that we use in the inference, so they're not exactly the same. And if you have large coefficients in that linear combination, it just becomes really unstable. So while in theory, you might be able to get better inference by including more of these matrices, in practice, it doesn't seem to be the case that we can do that. Yeah. So you need to decide on which of these motifs do you basically want to cancel out. You can cancel out one, but if you're trying to go to more than one, then at least, like, numerically we couldn't get better accuracy by canceling out more than one, because then other things about the method became wonky.
Okay, interesting. Is that in the paper, or is that just from your own experiences?
That's from the experiences. So we didn't include that in the paper. Some things are left for the reader to discover.
I like that. No, I was just wondering if I'd find more detail in there or not. Okay, next question. Just scanning if anyone's got anything, just jump in or throw your hand up. I wanted to ask you about, you mentioned sort of a default method, that was in one of the toolboxes, which was basically inverting the autocovariance matrix. Now, that's something that I'd seen before and always meant to go and dig into and have a look at, but I don't know it as well as I should. First question on that is, with that inversion of the autocovariance matrix, my gut feeling is that only works if your connectivity matrix is symmetric. Do you know if that's correct or not?
Yes, you can only derive that. So it only comes out as the proper solution if your matrix is symmetric.
Right.
So you can use that to infer symmetric matrices. If you assume that your network is going to be close to symmetric, you might just use it and say that, well, we're not going to get a perfect inference, but we're going to get something close enough. And it is something that you see. I think I haven't put them up, but so we have a plot like this for edge reciprocity, where you see that all of these methods, most of them do okay as you have more or less bidirectional edges in your system. But the OUI, so the Ornstein-Uhlenbeck inference, that just tanks as soon as you go to networks that have a lot of unidirectional edges in them, simply because the method can literally only output undirected edges.
Sure. Okay, so that's OUI on this graph.
That is OUR, yes.
Yeah. And so what was the baseline? What was the plot, the line?
So the baseline comes about from the fact that we have an oracle telling us how many edges we already have. So we could also just choose that number of edges at random. And in a network that is really sparse or really dense, already knowing that you have 90% of your network occupied or not occupied by edges already gives you a fairly high accuracy. So that's why we included this baseline over here to show that, for example, in this case, if your edge density is very low, all of these methods infer the networks with really high accuracy. But if you would have just guessed at random, you would have already gotten about 80% accuracy already. So you got to see it in relation.
I think I'm misunderstanding the what this baseline is. How could you get 80% accuracy at 10% density just by guessing? I'm understanding it.
So if I know that for every pair of nodes in my network, there's say a 99% chance that there's no edge between them because my network is really, really, really sparse. Then whenever you ask me, is there an edge? I'm just going to say no, 99% of the time.
Right. So
and I'm going to be right a lot of times.
Yeah. Okay. See, I see what you're getting. You're counting it as correct if there's no edge and it doesn't infer an edge.
Yes. Yeah.
Okay. Yeah. Got it. Yeah, just along the lines of the existing Ornstein-Uhlenbeck inference. I know a few people have tried to sort of take it a little bit beyond that before, but I'm not that familiar with what they've done. I'm thinking of, have you come across the work of Matthew Gilson at all, or even some of Peter Robinson's work?
I haven't, no.
Tried to do. I mean, they definitely didn't do the same thing. I know they didn't go into motifs. So I'm just curious as to whether there were any crossovers. Ben, do you know any of the details of what Peter did on that?
My Peter?
Yeah, your Peter.
Has he worked on this?
Not exactly. Like on that basic Ornstein-Uhlenbeck inference that we're talking about, that just inverts the covariance matrix.
Oh.
I know he had some things that we're looking at tweaks to that.
Yeah, he was using like Feynman diagrams to look at longer, different. Yeah, let me find it. I'm not going to say it right.
Is Peter a physicist by training?
Yeah.
That sounds. Maybe Peter and I should talk then. So I've given a version of this talk somewhere to a crowd of physicists, and somebody told me, "Oh, you're basically just computing path integrals."
Right.
I was a bit skeptical about that because it seems to be a physicist thing to say, "Oh, whatever you're doing, it's really just something that physics has done already 30 years ago, 50 years ago."
Correct. Correct.
And that particular physicist didn't then have the time to explain to me why what I'm doing is equivalent to computing path integrals. So I don't actually know if it is, and if it is, I don't understand the connection. But I would love to talk to somebody who knows about this stuff to see what the connection is.
I'm sure it's not going to be the same thing. Like there's no way it's going to be the same thing. Like I know the work of those two people I just mentioned, they're definitely not looking at motifs and using that knowledge to help it. I'm just wondering. I know they put some enhancements on the AUI method, and I'm just wondering whether any of those have a relationship. I'll dig out what I can on those and send them through.
Yeah, thank you.
I put it in the chat. I can share the bit if you want to see it. Like that's the diagram, right? Where you've got the direct path and then the, higher order paths. And in the Feynman diagram, that's called addressed. When you sum lots of smaller contributions, that's addressed propagator. But it's not thinking about it in this way. It's not thinking in the network inference setting. It's not thinking about dynamical processes playing out. It's just formulating higher order connectivity.
Like those
Taylor series of
Yeah, those diagrams, they look like network diagrams, but they're not, right? Like they are components of a covariance matrix, aren't they? Or are they? God, I don't know.
He is thinking in the same way, but he would be using completely different language. So someone who could translate might actually find some use.
So one thing that I've been working on recently with some people here at the University of Vermont was to try to get the process motifs working in some sense on nonlinear systems. As I said earlier, that's like strictly speaking, it's not possible to do it at all. But there's always something that you can do with like linearizing left and right and to get to something that is non-linear-ish. So what we have is a time-dependent Jacobian. So we have some sort of linearization in there. And what we did was for some examples of nonlinear systems, instead of looking at covariance, which only makes sense in stochastic systems, we looked at the importance of walks of certain lengths to how the system evolves over time. So you can, for example, show that if you're interested in what happens in 5 seconds, these are in the network structure, the walks that are going to be relevant for that. And if you move on to 10 seconds, then it's going to be longer walks or something like that. So, and maybe that would be more of the same, because there the quantity that we're looking at is not a covariance matrix, but might be, so in the screen that you just shared, it said something about a propagator,
right,
which I think might be the same thing. So maybe in that setting, those things would match.
Yeah, that could be interesting.
Yeah.
I don't understand it that deeply, this paper, or at least not anymore. But I put the link in the chat if
Thank you very much.
Yeah.
I'll look at it.
Okay.
Cool.
Peter's your postdoc, you said, or was your postdoc?
Peter was my supervisor, who's retired, whose retirement made way for my position. So
Okay.
he's like a father of, but he does neural field theory sort of stuff. Yeah. So dabbled in a bit of this. Yeah, he doesn't think about statistics or stochastic processes in that deeper way, but yeah, it's a good thought, Joe. Maybe there's something in that way of thinking about it.
Yeah, that's the thing. Like it's not going to be the same. Like it just isn't. But there may be some useful connections to help bring out in the discussion or things like that. Maybe.
Or at least have a shutdown ready if a physicist goes, "Oh, it's all just propagated." You can go.
Yeah, exactly. All right. Shall we leave you there, Alice? I should probably run and move on to the next meeting shortly. Let's thank Alice again.
Thank you. Thank you for having me. This was super fun. I wish I could come in person for snacks, but it's not exactly close, and it's the snacks are going to be cold by then. But thank you so much for having me. This was fun.
We'll send a cold snack in the mail, maybe. You hope it is disgusting.